You're listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Extrude with confidence, custom extrusion equipment designed for you and your application.
Hello, everybody. This episode of the podcast will focus on Nitinol for medical devices, including laser and post-processing. Our guest is Jose Maeso, CTO and Co-Founder of Lighteum. Lighteum's core focus is to deliver white glove customer service to the Nitinol medical device market. I hope you enjoy. Jose, thanks for carving out some time to join us on the MedX podcast today.
Thank you, Steve.
I'm really excited because I'm super interested in Nitinol, and I know a lot of other people are too. It's such a cool material because of its super elasticity and shape memory characteristics. But beyond that, tell us a little bit about the unique properties of Nitinol that make it an ideal candidate for medical devices such as self-expanding stents, heart valve frames, and flow diverters.
Yeah, so first of all, thank you, Steve, for the time. We're super excited and happy to, share a little bit about our special metal with the plastic community. I think it's awesome what you guys are doing, embracing the plastic and the metal together. So we love it. So thank you for that. First, Nitinol, you just call it the super elasticity. And that's why, we bring some samples in here just to show, that, right? Because it's not the same way just talking about it than seeing it. So this is an example of a Nitinol cut hard valve frame. And when we say super elasticity, this is what we meant, right? It's super elastic, so it's really, really flexible. And right now, this one, we imparted this shape, right? So it's in this shape that it's to create radial force to a vessel. The really cool feature, too, that we love to show people about Nitinol, right? It's that, when you cool it loses elasticity. So it will maintain whatever shape you put it in. But once you put it in hot water, it will just, retain the arena condition. And this is really exploited this on the medical device arena area, because that means that you can package this device on a really small microcatheter, and then it will navigate to the area that it needs to get the delivery. And then it will expand and create radial force to the device. So in hindsight, right, in other terms, it's like super elasticity, corrosion resistance, and you name it. There's a million applications for Nitinol. That's obviously what we're going to be talking about this. But yes,
yeah, that example you just said, where you can maybe crimp it and then load it into a sheath and then deliver it. Is that kind of what you're talking about for an example?
Exactly, right. So, catheters, and especially for you guys, the, extrusion guys, it's always round, right? So we will, super cool this device. We will crimp it into a microcatheter, right? So then the doctors can deliver this life-saving device from the legs, right? Or from the arms. They will go all the way from the leg to the arm to the heart or to wherever the device is going to be set or used. And again, the beauty is that you can compress it. It can be packaged tight into the catheter. And then we don't need a balloon to expand this. It's self-expandable. That means that when the doctor deploys the device inside of the body by itself, it will fill that space and it will create radial force around that area, opening up a vessel, anchoring something. The sky's the limit. Again, this is just more example of Nitinol parts that we, make here in Lighteum. This will be another example of a robotic assisted surgery type of device. You can see how it's super elastic, right? But if I pull it down, it will stay on that shape. Then I put it in water.
Yeah.
It's going back.
Wow. Very cool. Some of these unique properties that you just gave a perfect example of this, shape memory. Are there limitations to Nitinol? And traditionally it's been kind of high cost and maybe more used on more advanced modern applications. Are there any limitations related to Nitinol, for instance, such as cost or technical?
Sure, and it's funny you ask that because nitinol, even though it's an older alloy, right? It's been on them in the industry already for a long time. Still, nitinol is the new nitinol.
Mhm.
Like they are doing so much development, and we're just scratching the surface of the applications of this beautiful metal. And the limitations are cost, but as it gets more embraced on the industry, cost is going down.
Mhm.
For example, a couple of years ago, nitinol was only being used for the therapy given device. For example, the heart valve, the stent, or whatnot,
Mhm.
but not the delivery system due to the cost. But it has been, embraced way more on the industries being added to the delivery system. So I will say to your question, obviously cost, but it's more knowledge, right? That's why we're bringing the open door and we're open the box to all this knowledge base of national, because we want the industry to know how we make this device, the application out there, so they design for it, because it's just beautiful with a lot of applications for medical. And again, it's the cost and the know-how.
Okay.
I think that the metal especially has been always a black box, so that's why things like this will open up doors to engineers to design more therapy given devices with these alloys.
Jose, I love that, philosophy that you have, kind of an open door approach. And I might have to take you up on that and maybe take a visit and see your operation. And maybe we'll do some live videos of some of the processes, laser processing. That'd be awesome.
We would love to get you here and actually come and form an electropolishing part with us. That's what we love to do. We love to train people. We love to educate our customers on these, metals, so they design better, parts and exploit all these, nice features that it allow us to do.
Okay. Quick question on adding features to nitinol components, wires, hypotubes. Is it possible to add features? For instance, can you centerless grind the distal end to add some flexibility? Can you flare or flange the proximal end for maybe a connector of some sort?
Yes, that with natural, definitely the sky's the limit. Again, I'm gonna bring the same example. This
Yeah.
is the tube that this ball frame was cut. So you can see how, on the end shape, we have all these tapers and, you name it. We can even make the metal behave completely different by selectively heat treat some areas. So that means that that specific location will have a look and feel completely different than the rest. For example, the designer wants this top part to anchor on a vessel harder than on a bifurcation or something like that. He can change it, or he can say, hey, I want the stiffness of this area, higher than the other. So we can selectively heat treat only that area. So the feel of the device will be, different. So that's why, it's so important just to educate customers, because we want to make smart devices when, you can control how this metal behaves on the body by doing different, techniques of heat treatment, laser processing, electropolishing, you name it.
Okay. Wow, that's interesting. So you can selectively alter the properties, maybe ductility or stiffness along the length.
Yeah, so right now, when we hit street apart, right, the whole entire geometry is set up on a tool, and it's hit by three, techniques that we have. It will be a fluidized bed. It will be aluminum oxide just to get fluidized. The temperatures range from 530 C to 550 C.
Mhm.
We also have a salt bath where it's the same thing, but it's just molten salt and typical furnaces. So we will constrain the entire part on a tool, then put a subject it to that temperature, then quench it. That will make the entire geometry, change the metallurgical composition and the how it will feel. And you train also the shape memory to that.
Mhm.
But if we want to selectively heat treat or change the geometry or the feel or another location, we will take the part out and we will selectively with the lasers put heat on a specific location and then rapidly quench only that area. So then the whole frame will have a field minus that area, right?
Hmm.
Because they wanted to expand to the vessel, like you name it, right?
Interesting. Let's talk a little bit about nitinol versus stainless steel, and if you can, when is it advantageous to use nitinol versus stainless steel in a device?
Steve, when you need super elasticity, right? So we process both alloys, right? Because the lasers, obviously we cut a lot of stainless steel too, right?
Hmm.
So obviously the cost is a big driver of going nitrile to stainless steel, but stainless steel will always have a home on the medical device market, right? Because again, we can talk about it forever, but
Yeah.
the main difference will be super elasticity and shape memory. If
Okay.
you need super elasticity or you need to create like a special shape, then obviously not always your key. If it's just, if you just need access or you're creating an aspiration catheter or something like that, then stainless steel it's more than capable of performing any of those tasks, especially when you combine them with all the polymers and all that new technology that is around there. But
Okay.
not at all, aside from the cost, and the cost is
Hmm.
going down, what is being embraced more and more and more on delivery system. It's just a notch above, obviously, stainless steel, and just in capability wise, right? It's just
Yeah.
again, it's a beautiful alloy. There's no other word for it.
Can you leverage the advantages of nitinol and stainless steel by joining them together in a laser welding process?
Yes. So there's several techniques to autogenously, that means without adding filler material, weld wires, and there are some wires commercially available with that technology. It's just it's super hard to do it repeatedly,
Hmm.
and it's really hard to do it on something that is not a wire. What the industry is doing, it's obviously doing some mechanical laser cut fissures that you can attach to both alloys, or oh, another item that is changing a lot is that because of the price of naturals going down,
Hmm.
a lot of times it doesn't make any financial sense to mix them, right? Aside from mechanical mixing. But with that being said, there's processes out there to do it autogenously. There's other processes where you add a third metal, any nickel, high nickel alloy, to sort of like help with the metallurgical transition between the two alloys, because they're just not weldable, autogenously easily. But with that being said, there's other alternatives like mechanical bonding, grinding, and
Hmm.
whatnot.
Okay. I know that nitinol can be heat sensitive during processing. And for that reason, is there a particular laser processing technique that's used, for instance, femtosecond versus long pulse, to kind of uh, ensure that you maintain the physical properties?
Yes. So as we discussed before, when we heat treat or when we train the shape memory of Natinol is with heat, right? So just by that notion, obviously, when we want to cut it, we don't want to put heat because it will damage the metallurgical composition of nitrogen, right? So what we do is that we process this alloy, or we cut it with femtosecond lasers. And when we mean femtosecond lasers, just the pulse width, right? So the pulse width, every pulse of the laser, it's a femtosecond, it's 800 to 600 femtoseconds, which is small enough that the material doesn't have any time to react. Basically, when the photons collide with the metal, there's no time to convert that photonic energy into heat. So it goes straight to plasma. So that's when we, ablate this part. That's a term that means
Hmm.
just basically processing without heat. We get these cuts full of like this ablated dust on the surface. And why we do that? Because we don't want to thermally damage this material. On the other hand, why when you weld, you need heat. So That's the confusion, right? Welding lasers, they need to impart heat in order to be able to fuse. Cutting lasers, you want to put a a little heat as possible. The you know the not the problem. The always the debate on the market is that there's two technologies:
Mhm.
longer pulse cutting lasers, where they're called fiber lasers. And by the way, that's something that we do a lot here in Lighteum. Just basically educate our customers on what's the laser technology, because that's really important for them to know, what technology is best suited for the specific application. For example, for cutting stainless steel, fiber laser or longer pulse laser will make more sense due to the cost, right? Because you'll
Mhm.
be able to cut faster because the average material removal rate it's way faster on a thermal system or thermal laser. But then on the femtosecond laser, it's like it's like basically like comparing a blowtorch to a surgical knife, right?
Mhm.
So the femto, you're just going fast, you're cutting, it's really cost effective for stainless steel or for any alloy. Then heat affected zone is not that important. Or you can post process a lot. That means that you can remove all these heat affected zone by mechanical methods or chemical methods. Then it makes sense. But when you need specific features and extreme control on accuracy, then you want the high power femtosecond lasers, and that's where we're experts here in Lighteum on processing that with these type of lasers.
Interesting. You talked a little bit about speed, and I'm wondering when you work on a development project from R&D and go to V&V to commercialization, talk to us a little bit about scalability of that laser processing technique.
Sure, I think what we do a lot is when we start working with the new programs, we ask always the customer what in what area of the development cycle this program is, right? Because you need to plan ahead for scalability, right? It's not the same developing a process for doing 500 parts a year than millions, right?
Mhm, mhm.
And it's not the same also to do a delivery system part that's a single use, that creating an implant that it will have electropolishing, passivation, and you name it, because it's just the therapy given device. So what we do is that obviously we want to be there first. We want to know what's the volumes and what's the timeline for this device, and then planning ahead with process development, validation, and whatnot, so we can develop steady and stable processes so they are repeatable, right? And that's where when we start with the right technology and the right design, it will just flow. I know that in this industry there's not a lot of time, right? It's go go go, but that's where a lot of time just experience matters, right? Just
Yep.
be putting processes or on the line before it's the best school for doing it afterwards, right? Because you learn so much by doing all this process validation, by doing all these studies, that there's no replacement for experience on the laser cutting in natural world. Let's just put it that way.
You mentioned post processing. Let's turn our attention to post processing of nitinol after laser cutting. Why do you need to do that, and what methods are used?
Sure. So post processing is used basically to enhance the surface of the natural device. So to enhance performance, I need to give this, shiny finish that is not always shiny, right? It's just corrosion resistance, fatigue resistance, because you eliminate any micro crack propagation, because there's not going to be areas that cracks can start and then migrate, right? So after we do all the thermal processing, we will remove all the oxide, and then we will get the part to an electropolishing state. That electropolishing state basically, like I said before, enhance the surface finish and the corrosion resistance of natinol. And it will also round all corners, because a lot of times that's really important for the designer, because they don't want any sharp edges or corners to have any detrimental effect on the body, right? Most of the time people want, round, smooth surfaces. So the device will glide on the delivery system, and it will also, find its nice place inside of the body. So, and by I think 90% of what we do at Lighteum, especially on Nitinol, will get electropolish and then passivated.
Okay. The passivation is to prevent corrosion.
So even though Nitinol is, corrosion resistant, naturally, it will build a toxide layer just by being on the air, by being exposed to nature. Like, we want a thick homogeneous oxide layer, so we will use the last step. We'll use a nitric or any mild acid to build that oxide layer, so then we improve the corrosion resistance by a lot.
Okay. I was wondering, are there any techniques used to modify the surface, the outer surface, I think, or the inner, of a laser process stent to improve bonding with like a polymeric cover, like a expanded PTFE, or maybe even a drug carrying polymeric coating? Is there anything that would enhance the bonding characteristics between the polymeric cover and the stent?
Yeah, yes, that's a technique typically used, right? So we will use the laser to cut the geometry, right? To laser cut, but then we will put the part after it's been processed on another laser system that it's a lot less power. And instead of manipulating the part under the laser, we're manipulating the laser in top of the part. So layer by layer, we will change the surface morphology of the device to to whatever the designer needs to put on the surface, right? We can make it hydroscopic, we can make it so it adhere, increase adhesion, you name it. But yes, it's a subsequent step, but that is the beauty of the laser, right? The lasers these days are so controllable that we can control the photons to be strong enough to cut through the material or just to change the surface morphology of the material.
Ah, interesting. Very interesting. I had Dan Kasperzik from Poba Medical on season 1, and they're a developer of novel balloon technologies. And Dan was telling me about some development work he's doing to add micro surfaces to the outer OD of a balloon to create traction or grip with between the balloon and an inner body lumen. So is that the same idea? You could potentially add some micro surfaces to increase grip as well.
Yeah, the laser don't know the difference, right? It
Yeah.
just, it's just a matter of finding the correct wavelength, the correct technique in order to create the desired surface effect. But yes, it's exactly the same technology. And that's the beauty of the laser, right? When you can use the same technology for polymers and you can use the same technology for metals. And that's the beauty of like high power femtosecond lasers. The the control on the photons are it's so tight and so great these days that they're almost these days impervious to different metals, to different polymers. It will just ablate.
Yeah.
Obviously everything has limits in life, but we're getting to the point that the technology is there and the power is there, and there's multi-wavelength lasers. We can talk about it forever.
Yeah.
That's the problem.
Okay. We want to talk a little bit about some trends we're seeing in the industry related to nitinol. And you kind of touched on that earlier, where in the past, maybe just the device, a stent or a heart valve frame would be of nitinol, but you're seeing more nitinol components, metal components in general, being used in delivery systems, core wires, braid wires, and whatever it might be. Talk to us a little bit about that, or maybe other trends you're seeing as it relates to nitinol and medical devices.
Yeah, well, like you said, we, first it was only used for the therapy given devices, right? Because it was because that's the only part of the delivery of the system that allowed to spend the money because the cost was higher on the device. But now with the prices of nitinol going lower and also the industry really embracing the technology, again, we're seeing a lot of embracement on, robotic surgery, right? Just because of this, nice features that you can do. You can do super elasticity. You can change, how it feels distally, proximally, you name it. So it's mostly that. And then on the catheters, right? Before only nitinol was used maybe on the braiding, right? It was braiding nitinol in order to give stiffness. Or now it's just a combination of maybe braiding, maybe tubing, different polymers, ablation, and again, maybe doing different heat treatment techniques. For example, you can have a long, delivery system parts that distally will feel completely different than proximally. Why? Because of maybe grinding techniques, thermal treatments. We can polish a certain area. We can make windows. It's just that's why we love lasers combined with nitinol and polymers, because the sky's the limit of the application, especially for medical devices.
I love it. I love your enthusiasm too, related to nitinol. It's awesome. So glad to have the opportunity to talk to you about this. And want to wrap things up and just talk about a stocking program that you have for nitinol. We've seen in this space more access for components, whether it be medical tubing, nitinol, a wide variety of components that you can get through online stores and have them on your desk within days. So tell us a little bit about this nitinol stocking program that you started recently.
I think we all got accustomed to the Amazon treatment, right, Steve? Like we want to click, and get instant gratification, right? So we're trying to get almost the same model on the medical device industry per se, but just mostly on the R&D phase. The problem years ago was getting the raw material for us to start processing parts. It took a long time. So mostly developers were relying just on computer simulation and models before they actual, get upon their hands. So what we're trying to do is, turbocharge this development from, design to actually getting a part in your hand. So what we're trying to do is, when the designer gets, the first, concept that he wants to do, we want to have tubes in-house. So in the matter of days, we can put a part on the designer's hand instead of them, just playing with computer simulation for month and month and month. Then you get the first part and it feels completely different than the intent. Because all the computer models, they're just as good as all the assumptions, right? So nothing beats to put a part in your hand really quickly. So that's why we have, more than 2,000 SKUs of, raw material nitinol in hand, because we want to be able to get parts to the designers within days. So then, you can quickly change the design and make it better. Or, then we can go and do the production run subsequently. Because what happened on the past is that, when a designer came with an idea and they send it to the contract manufacturers around to get quoted, if, the quote back was 6 months, that idea is going nowhere. Because if you just want to test the concept, you have to wait 6 months to get a part on your hand to put it maybe in hands of a physician to get feedback. It just kills, innovation. So we want to fuel innovation, and that's why we have material in stock, so we can, get parts in a matter of days.
Excellent. And you said 2,000 SKUs. That's a good start.
200 SKUs. Sorry, 200 SKUs.
Okay.
We wish.
Yeah. Awesome. Hey, Jose, this has been a great conversation. Thank you so much for joining and sharing your thoughts and knowledge on nitinol, and we'll continue to get the knowledge base out there and educate the industry.
And I Steve, an open invite. Like, I would love to get your hands dirty with nitinol. Like, it will change from all your polymeric experience to start, heat setting and polishing some parts. And we want you to actually cut up on the laser. That would be pretty cool.
All right, I'm going to take you up on that.
Awesome, Steve. So again, thanks for your time, and we'll keep on rolling.
All right, thank you.
Thank you for listening to MEDX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.